Okay, so here we go with the third of our optional examples classes on definitions, proofs and examples. And today we're going to start with examples. And these examples, there are three questions about examples, and of course first of all you need to know the definition of the terms, and then you need to be able to think up some examples. And these examples are designed to show you, just like the kind of thing we've been talking about occasionally in lectures, that something could be true for one set, for two sets, for three sets, for any finite number of sets, but go wrong when you put infinitely many sets together. Or, I mean, in lectures we had that if you took open sets, and if you took finitely many open sets and intersected them, then you'd still get an open set. But we found out in lectures that if you took an infinite sequence of open sets and intersected them, then what you had left didn't have to be open anymore. Well, here are three very similar things, and I'll just remind you what the terms mean. A finite set is one which has only finitely many points in. So it doesn't mean bounded, though it is true that if you're finite, then you have to be bounded. That implication is true. But a finite set means you've got finitely many points in. Bounded sets, we've done loads of examples by now, so hopefully everybody knows what bounded sets are. And closed sets we did more recently. So the first one you're going to have to think of some finite sets, but by the time you put them together, you've got an infinite set. Infinitely many points. The second set, that's not enough, though you may well find an example that works for both. You may well want to look for examples that work for one but not for another, or another example that works for both A and B at the same time, just so that you can make sure you know the difference between finite and bounded. So the bounded one, you've got to find some bounded sets, a sequence of them, and by the time you take their union, what you've got left, what you now have, is not bounded anymore. And part C, you have to find some closed sets, a sequence of closed sets whose union is not closed anymore. And I told you in lectures one way to do this, which was to take the open sets that we did, the problematical open sets we had in lectures, take their complements, will give you some difficult closed sets. But you can find lots of other different ways to do it. And it's also possible to go wrong as well. So you have to make sure that the final set you end up with really isn't closed. It's not enough to say that it doesn't look closed. It really mustn't be closed. You're allowed to use the sequence criterion. If you've figured out the sequence criterion, you could use a sequence criterion to show something isn't closed. All you have to do is find one sequence in the set that converts it to something outside the set. So you could use a sequence criterion. I think I probably will, to show you how that works. So you could use the sequence criterion to help you to show that the final set is not closed. So as I say, if you're going to do it that way, then whatever your final set is, you're going to find some sequence in it that converts it to a point outside of it. And that will demonstrate that it's not a closed set. Okay, I'm going to let you think about all three of these, and I'm going to come round and see how you're getting on with it. Okay? Now, where's my pause button? Okay, I've seen various correct examples for A and B. So, let me do you one for A. In A, you could take AN to have just the point N in it. That's only got 1 point, so it's definitely a finite set. So that's 1 point. Then if you take the union of those over all natural numbers, you get all the natural numbers. This is the same thing, by the way. Union from n equals 1 to infinity, that's the same as the union over all natural numbers. So that's just two alternative notations for the same thing. And of course, you just get all natural numbers. This, by the way, is because naught is not a natural number, otherwise you would have had one extra term in your union. But naught is not a natural number in this module. and that's an infinite set. So AN are clearly finite, each finite, so there's 1 point, but the union of the ANs, which is n, is a standard infinite set. Now, rather boringly, that works for B as well, because these sets are bounded and the union is unbounded. The same example works for B. A set with 1 point in it is definitely bounded. Can't get much more bounded than that. But by this stage, I accept that if you take all the natural numbers, that's clearly an unbounded set. Which brings us to C. Oh no, let me give you one more example of that. And I think I'm going to need another page. Suppose you want an example that works for B and not for A. You could, for example, take the closed interval from -n up to n. That actually is a closed ball centered on the origin, so that makes it bounded. Then AN is bounded. But the union of those is a whole real line, which is unbounded. Okay, so that's two answers to B, and that one has the advantage that it doesn't work for A, in some, if you call that an advantage. So this example does not work for A. Because those are bounded sets, but those aren't finite sets, so you couldn't use that one in A. So what about C? Closed sets. Anyone got any ideas for this one? Anyone come up with an example that might work? Just ideas, it doesn't have to be right. Any suggestions on some closed sets whose union might not be closed? It's quite easy to go wrong here by ending up with something that looks like it might not be closed, but it turns out to be. The two examples I've given so far don't work. The examples I've given so far, all the sets involved were closed, but the union was closed as well. The natural numbers is closed, so that didn't help us because we wanted a union not to be closed. And the real line is closed, so that's no good. But we wanted an example where the union wasn't closed. So the two examples I've given you so far don't help. We need something else. Did anyone have any ideas to how you can get into trouble with the union? If not, I'll just give you one way to do it. There's lots of different ways to do it. Here's one example. We'll consider this time AN will just have 1 point in, but this time it'll be 1 over n. So the A1 has just got 1 in it, A2's just got a half in it, and so on. So these single point sets, finite sets, it's standard they're closed. So it's standard that finite sets are closed. So each AN is closed. But this time something different happens when you take the union. So the union over all natural numbers of the AN, which is the union from n equals 1 to infinity of AN, is 1/2, 1/3, and so on. But note that naught is not in this union. Let's call it something. So we're calling it A, and we note that naught is not in A. Remember, to be in the union, you have to be in at least one of the sets. And of course, naught is not in any of the sets we looked at, because we're only looking at sets AN where n goes to natural numbers. We're not dividing by infinity at any stage. So A has got all these points in, 1, 1/2, 1/3, 1/4, but it doesn't have 0 in it. Now we could use the sequence criterion as one of the ways to show that A is not closed. But then 1/n is in A, 1/n tends to naught as n tends to infinity, but naught is not in A. So A fails the sequence criterion for closedness, and so A is not closed. But of course, you can go back to your definition of closed, take the complement of A, and find out what the ninterior is. You'll discover that naught is the only ninterior point of A complement. So, or show that naught is in the nint of A complement directly, which will demonstrate that A complement is not open, and if A complement is not open, that's the same as saying A is not closed. So that's another way to do it. Right. And that's the sort of thing you have to do. You have to make something bad happen with some sort of limit point from something like that. And that's a typical example. Okay, so I hope I've given you some ideas of how you find examples in that sort of situation. Right. Now, the rest of this session we're going to look at proving things about absorption, which is this non-standard terminology of mine. And you're going to prove all these easy facts about it that I said were clear in the notes, and now you're going to get a chance to prove them. Okay, so what's this absorption thing? It's the one about getting stuck inside a set from some point on. So your set A absorbs the sequence if, after a while, all terms of the sequence are somewhere inside A. They don't have to converge to anything. It just says that they're in A somewhere. They may oscillate around like crazy inside A. As long as they stay inside A from that point on, then A has successfully absorbed the sequence. And if you want to say which stage it's absorbed it by, well, actually there's lots of different stages it absorbs it by, because if it absorbs it by a given stage, then it absorbs it by the later stages too. So we'll say it absorbs it by stage n means that at least once you've gone that far, you stay inside the set. It may be that you got stuck inside the set earlier, but we don't care about that. So that's what absorbs by stage n means. And here's the epsilon n definition of convergence for real numbers, which is somewhat related to absorption, as we saw in lectures. This is that for all positive numbers epsilon, which somewhere represents how close you're going to try and get to your limit, there has to be a point, a natural number n, large enough, implicitly large enough, so that as long as you go at least that far, your xn's will be close enough to your limit. Modulus the difference less than epsilon. So that's the definition of convergence we're working with today. It's a standard definition of convergence for a sequence of real numbers. So, let me show you some of the questions you're going to have a look at, and let's see how many of them you can do in the remaining time. First of all, that if a smaller set absorbs a sequence, so A is a smaller set, B is a larger set, probably. Suppose a smaller set absorbs a sequence, then prove that the larger set also absorbs the sequence. Completely easy, 2 lines long. Let's just check you can work with the definition. Okay? Then you get to prove the converse, which is maybe more fun. Now suppose that the result from 2 is true, that you've just got 2 sets you don't know how they're related. You suppose the conclusion, that is that every sequence that A absorbs gets absorbed by B too. Prove that that can only happen if A is a subset of B. So that's the converse to 2. Okay, if you've got through those 2, you can look at the next one. Which is checking what I told you about convergence and its relationship to absorption. The first one is that xn converges to x. You have to show that these are equivalent, so each one has to imply the other. So you want to prove A implies B and B implies A, usually. But in fact, in this case, so usually you would prove A implies B and B implies A separately. And usually one direction will be harder than the other. On this rare occasion, you can do A if and only if B directly. Because this one is proof by substituting in the definition and changing epsilon into R. That's all you have to do this one. You'll discover that you've got a dummy variable, and in one thing it's called epsilon, in another one it's called R, and you just say it doesn't matter whether it's for all epsilon something is true about epsilon, or for all R something is true about R. Then you'll discover by the time you've substituted in the definition of absorption, you'll find that these 2 actually read as exactly the same statement. So that's pretty easy. And then, if you do get through all those, this one's more interesting, and you should prove A implies B and B implies A separately for this one. This is one where instead of saying something happens for all open intervals, you say it happens for all closed intervals instead, which looks a bit different. So this is, this time prove A implies B and B implies A separately. Okay, now let's give you a chance to have a go at those, and we'll see how far you get. And I may not have time to prove all of them for you, but at least you'll have had a chance to think about these. Okay, let me do questions 2 and 3 for you to show you how this works. Question 2 is as easy as you think it is, but you do have to write something down. So since, let's get a pen. Since A absorbs xn, there exists a natural number n such that for all terms from then onwards, we have xn is in A. But A is a subset of B. So xn in A implies xn is in B, and we have xn is in B for all n greater than capital M. And so B absorbs xn as well. You have to write something. All we've used is definition of subset and the definition of absorption. Plug in the definitions. The proof really isn't anything other than saying that if you're in the smaller set, then you are in the bigger set. Okay, that's that one. So now I want to prove the converse. For the converse, I suggest using the contrapositive. We'll prove the contrapositive. Suppose A is not a subset of B. We'll show there's at least one sequence which is absorbed by A but not absorbed by B. Has anybody worked out how you do that? It's working with definitions again. Definition of A not a subset of B is there's at least one point in A that's not in B. So since A is not a subset of B, there exists a point A in A take away B. That's the definition of not being a subset. And now once you've got this point A, what would be a good sequence that is absorbed by the set A but is not absorbed by the set B? Any suggestions? We've got a point that's in A and it's not in B. And we're pretty abstract at the moment, so there's not much choice for interesting sequences to take. Any suggestions? No one brave? All right. I'm sure some of you got the idea here, but just don't want to tell me. You take xn to be the constant sequence A. That's a constant sequence. So not only is it absorbed by A, all the terms are in A. So it's certainly absorbed by A. Not only does it fail to be absorbed by B, it doesn't have any terms in B at all. So it's a really, really extreme example, and it's certainly the case certainly A absorbs xn, he doesn't. And we finished. We've proved that if A is not a subset of B, then there's at least one sequence absorbed by A that isn't absorbed by B. That's a contrapositive of what we wanted. So that shows that if every sequence absorbed by A is absorbed by B, then A has to be a subset of B. And so we finished. Okay. Let me pause briefly again and see if anybody's had a go at question 4. Okay, let's see how you do question 4. And we'll just substitute in the definitions. A holds by definition if and only if for all epsilon greater than naught there exists a natural number n such that for all n greater or equal to capital N we have mod xm minus, what are we trying to converge to? X, I'm glad to see. Mod xm minus x is smaller than epsilon. And, but it doesn't matter what the letter is, so I'll convert epsilon into r. It's a dummy variable. If something's true for all epsilon about epsilon, that's the same as saying it's true for all r about r. So that's even only if for all r greater than naught. Ooh, that should have said for all epsilon. So the first one was for all epsilon. We'll just change that into for all r greater than naught, and we'll just substitute in r for epsilon throughout. There exists a natural number n such that for all later terms we have modulus of xm minus x is smaller than r. But that one, modulus of xm minus x is less than r, that's just the same as being in the open interval, centered on x, radius r. So that's if and only if. This is all pure substitution, rewriting, doing nothing except trying to convert one statement into the other. And you could do this more efficiently by saying, you know, this first bit of the statement, I don't want to write it out 10 times. But anyway, I am writing it out several times for you. For all n greater or equal to n, we have xn is in the open interval x minus r up to x plus r. That's the same. That last one's the same. That xn being in there is the same as saying the modulus of xn minus x is less than r. That's exactly what it means for a real number to be within distance r of a certain point. You have to be in the open interval, in this case, open interval, centered on x, radius r. But now we regroup it. I put a bracket around that last bit. That bit I put in brackets there says that the open interval x minus r, x plus r absorbs the sequence xm. That's exactly the definition of absorption. So if you substituted that one in, you'd get to this. You could work from both ends and meet in the middle. And that's by the definition of absorption. We just substituted in the definition of absorption. And we finished. So I shall leave you to think about question 5, or you have to do a little bit more work. One of the directions is trivial, one of the directions is more interesting. I think we better stop there for this session, and we'll start the lecture at 3 o'clock.